Hello everyone, my name is Greg and I'm with the Berkeley SETI Research Center. And today I would like to offer you a brief tutorial on the manipulation of one of the various data products that are offered by the Breakthrough Listen program. And that's of course the raw files. So those raw files consist basically in the actual raw digitized voltages recorded by the Breakthrough Listen standard backend. And as such, because they're voltages, they possess pretty much all the information that is available at the output of a telescope. And they enable anyone to recompute, for instance, dynamic spectra at any given time or frequency resolution, depending on the type of science they want to achieve. Another advantage of manipulating those voltage data is the possibility of eventually applying advanced signal processing to SETI data to facilitate the search, for instance. So the data set I'm going to work with has been collected about a year ago with the Green Bank telescope in West Virginia, USA, shown on the left here. And the experiment consisted in detecting the currently farthest man-made object, and that's the Voyager 1 spacecraft. So you can find all the information that you need about the spacecraft on this website. I'll put the URL in the comments of this video. As you can see, the spacecraft is extremely far, 39 astronomical units from Earth. And it's still transmitting signals towards the Earth. Due to the distance, of course, the signals are extremely weak and very challenging for detecting them, even with a very large radio telescope. So this type of observation achieves two goals. The first one is the insurance that the detection pipeline that is running on the data indeed permits the detection of an artificial distant signal. That's of course what you expect with a SETI pipeline. It also works as a quality control to verify that the SETI equipment works well as it should be, that the frequencies are as expected, etc. So the standard equipment of the Breakthrough Listen program on the various radio telescopes that are running the program and the signal flow is depicted here in this cartoon. So the telescope data, the actual voltage, are first split into bands that are 187.5 megahertz wide. And each of those signals are then sent towards a Breakthrough Listen compute node. Those compute nodes perform a second stage channelization of the data to reach bandwidths down to 2.9 megahertz. And then finally, a recorder simply fills the raw files with the digitized complex samples of those coarse channels. And the rest of the pipeline, for instance, the generation of the dynamic spectra is not depicted here in this cartoon, but that's of course what happens right after writing the raw files to disk. And the rest of the pipeline should probably be addressed in future videos. So the structure of a raw file is pretty basic. So a raw file is simply a binary file. And it consists in a succession of blocks, each one starting with a header that summarizes all the parameters that are necessary for data handling and processing. So that's all the observation parameters. For instance, what frequency were we looking at, what telescope was used, what direction, who observed, etc. Then there's an eventual padding that might vary from file to file between the header and the actual channelized data. And this padding is not to worry about. It's simply an artifact of the write to disk protocol. And the size of the padding might vary depending on the size of the header, such that the size of header plus padding is an integer multiple of 512 bytes. So then after the padding, you will find the 64 coarse channels that are adjacent as shown here. So the astronomy receivers usually sample two types of polarizations, and those two types of polarizations, the two simultaneous samples of the voltage data, are simply intervened in each of the channels. The size of the channels is of course also indicated in the header as a keyword. The samples are complex, and real and imaginary parts are also intervened. And so yeah, that's pretty much it for the structure of the raw file. Now, an entire raw file doesn't span much time, much observation time. It's usually limited to 22 seconds at most. And its size approaches 16 gigabytes, depending on the bit depth of the voltage samples. I believe now 8 bits for the real part and 8 bits for the imaginary part is a standard. So those raw files can be downloaded directly through the Breakthrough Initiatives website that you see here. So I will also put the URL in the comment of the video. So the way you download this kind of data is if you really know what kind of data you want to process, you would pick the Breakthrough Listen at Green Bank. That's the radio telescope, one of the radio telescopes that are running the Breakthrough Listen program. There's also an automated planet finder here that's an optical telescope that is also running the Breakthrough Listen program. So we'll kind of focus on Breakthrough Listen at Green Bank. And as I said, I would like to process Voyager 1 data. So you can just go down, drop list, and pick Voyager 1. And you might want to indicate what observation you're interested in. So you can put the time here, the center frequency as well. That might be interesting because, of course, Voyager 1 is a pretty narrowband transmission. Its transmission is pretty narrowband, so you wanna not necessarily sample the whole observed spectrum for finding it. So you click search, and here is a pretty huge list of all the raw files that you can download. So you know that it's raw files because it says baseband data, and you have various parameters. For instance, when has the data been captured in MJD as well, what telescope, etc. So you can just pick the file that you're interested in. As you can see, there are plenty, and you click on the download, and that should simply download the file onto your desktop. So for the sake of time, I will not let this download running any further. I've already downloaded the file that I'm interested in, and I would like to offer you this tutorial that will consist in opening the raw file, reading it, and plotting a spectrum, and eventually detect Voyager if possible. So here I'm using MATLAB, and of course the code will be available as well, and can also run if you're not licensed with MATLAB. You can also use the software Octave that works exactly the same way, and the scripts can be run on Octave. So here's my workspace. I have my Voyager 1 raw file here, and I am going to simply open it. So this line defines the name of the file that I'm going to process. Here are other parameters that I'm not going to talk about now, but they will be interesting later. So I open the raw file, same way I would open any binary file, really. And what this first piece of code here does is simply reading the header and extracting a few information that are particularly interesting for this data handling. So I press F9, the code runs, and I think here in my workspace I see various variables. For instance, you can see the observation bandwidth that is 187.5 megahertz wide. It's minus 187.5 megahertz because it's possibly an even Nyquist zone, so it's reversed. The frequencies are simply reversed. There is an observation frequency that is here in megahertz, and it's simply the central frequency of the whole observation. So there are 64 coarse channels, and the central frequency is located between channel 32 and 33. The header itself, actually I recorded the whole header. I can display it. Here we go. So this is simply reading all the different lines one after the other of the header. So each line is made of 80 characters, and well, it's really easy to read all that. So there are a few information that are, as I said, interesting to note, to keep in mind. Notably, for instance, this value that is called DIRECTIO. And earlier I mentioned to you that there is an eventual padding between the header and the actual data. This padding is indeed present in the raw file if this variable is set to 1. So now we know that we have to take in account a padding. And I take in account this padding with this smaller piece of code here that simply checks if the variable DIRECTIO takes the value 1, then we assume that the size of the header plus padding is, as I said, an integer multiple of 512 bytes. All right, so I know I know the complete bandwidth of my data, and I know the central frequency. So I can compute the lowest frequency of the band and the highest frequency of the band. It is important to note here that the highest frequency is actually the lowest because, as I said before, the observation bandwidth is negative because it's an even Nyquist zone. Those two lines of code simply measure the size of the raw file and divides this size by the total amount of data that's contained in one header and one padding and one data. So everything is available, and so that tells you how many data blocks you will have in your raw file. And then here we go. Pretty standard. What I'm going to do now is plot complete spectrum of the file, of the raw file. So because it's so much data, I will limit myself to just reading one block of data, but all the different coarse channels. This is what I'm doing here. I'm going to run the code first and go over it after that. Okay, so it seems that I haven't run those. All right. Here we go. Shouldn't take too long. Okay, here we go. So what you see now is the 64 coarse channels that I mentioned to you, and the two polarizations as well. And as you can see, it looks pretty empty. We see a lot of peaks, and those peaks are simply the frequency, the zero frequency of the Fourier spectra of the data. They just consist in the DC term of the signal itself, and they absolutely not to worry about. you see the shape of the bandpass of the receiver and the total signal path. That's giving a little bit of a shape to the spectrum. So this is the power spectral density, by the way, in dB as a function of the frequency. And it's a bit unfortunate because it looks like there's no Voyager in those data. We would expect like something much more like a peak. Well, turns out I know this data set and I can find Voyager very easily. Here, those 3 peaks are the transmission, are the fingerprints of the transmission of the spacecraft Voyager. Now I know it because I've done further processing of this data. As I said, here I'm processing just 1 block of data. So that's 22 seconds divided by 128 blocks. That's the number of blocks that are in my raw files. So that's not much data. And of course, you get more sensitive with integrating for a longer time. Now, do we see it here? Not that much. We might see a little peak here, but there's not much as you can see. The transmission is actually pretty much polarized and pretty much present in only 1 polarization of the data. All right, so how did I plot this spectrum? So as I said, pretty easy if you know how to read a binary file. So here I'm doing simply an fseek for going to the block that I'm interested in. I skip the header, and then I read the channel that I'm interested in. So here I'm looping over the different channels at one given data block. Once I reached the right place where I want to be in the file, I read the whole chunk that corresponds to the size of one course channel. So this I know from the header that the data are the bit depth of the data is 8 bit. So this is the reason why I'm reading this amount of data in integer 8. It's signed integer, of course. I reshape my array into 2, and what that does is simply it separates what's real and what's imaginary, and then I just sum up real plus I times the imaginary part. And here we go, we have complex data now. And then I keep reshaping, once again, the data so that I can also isolate the 2 different polarizations. Now for one given polarization, what I'm computing here is an average periodogram. So the average periodogram is basically cutting the signal in smaller segments, applying a Fourier transform, taking the squared absolute value of this Fourier transform, and simply averaging all the segments together. And this provides you an unbiased estimate with reducing the variance as a function of the number of segments that are averaged together. I'm doing the same thing exactly for polarization 2. And here it's just a matter of what's the frequency, the lowest frequency and the highest frequency of the channel that I've been working on, and I'm plotting in the loop all those different subspectra, spectra from the various coarse channels. So okay, we have plotted this, and we've seen 3 peaks, and you might not even believe me that there was a Voyager. So let's try to do something else. Again, what I've been doing before is just looking at one single block of data and plotting the spectrum over all the coarse channels. So now what I'm going to do is focus on the coarse channel where I'm expecting to find Voyager, and read all the blocks that correspond to that coarse channel. And once again, I will do an averaged periodogram, and that's supposed to increase the sensitivity of the data processing, and make it easier to actually detect the signal. So I just clean a little bit my workspace. here I know that my channel, my course channel of interest is course channel number 7. I know this because I know what frequency I'm supposed to find Voyager at, and I know the frequencies of my raw file. So I know that I would like to focus on this particular channel, and that's just channel number 7 in the order of the raw file, in the structure of the raw file. My resolution, my frequency resolution that I would like to achieve in this experiment is 2 to the 14. That's already it's up to you to pick what frequency resolution you want to achieve. So that just means that over a course channel of 3 megahertz, 2.9 megahertz, I will have 2 to the 14 frequency samples. All right. Once again, I define fname, the name of the file, of the raw file that I'm interested in. I open this raw file as a binary file, and just to make sure that everything is still fine with the data themselves, I reread the header. So it's exactly the same header, the same file as before, so no reason why things would have changed. Here I'm defining again the lowest frequency and the highest frequency of the complete raw file. It's not necessarily when you want to focus on one course channel, because you're particularly interested in what the frequencies are for the course channel. But I just find it easier to also calculate the lowest and the highest frequency of the complete band, and then I can easily find the limits of the course channel with simple arithmetic from those two values. This value here is the bandwidth of one course channel. As I said before, it's 2.9 megahertz, and I'm just double checking it with dividing the total observation bandwidth of the raw file divided by the number of channels that we have. So that's my own notation. I know what I've been doing. Of course, you're welcome to change your notation. And have I run? Might not have run this. All right. So nCHANOI is indeed minus 2.9 megahertz. It's once again it's minus because of the Nyquist problem. Okay, I'm not sure how many blocks I will encounter in that raw file. That's particularly interesting here, or particularly necessary to compute, simply because I will actually read all those different blocks. So I want to know when to start and when to finish. And as I said, most of the raw files that you might download will have 128 blocks. It's possible that at the end of the observation, a full raw file will not be recorded, and therefore there will be less blocks. So it's always a good practice to double check this. And then, okay, I'm pretty much doing exactly what I've been doing before. So reading this time all the data blocks for one given channel, as opposed to all the channels for one given block. And let's see where we're gonna find them. Okay, it seems that it's been working. Right, okay, let's just plot. So what you see here is the waterfall plot that I generated with MATLAB that corresponds to one single raw file, so only 22.9 seconds worth of data. So you have here, oh, this is not the power spectral density, this is the time, this is the block number, and this is the frequency. I'll fix this very rapidly. And of course all this code will be available to you. Yeah, block number and block number. And here we go. So once again, you don't see much. It seems like a pretty empty waterfall plot, unfortunately. But the reason why it looks so empty is that the frequency resolution that I asked 2 to the 14 is pretty big. So it has this advantage of reducing the noise level, the power spectral density of the noise, because it's averaged over lots of frequency samples. But those frequency samples are so thin that you might not, at a first glance, see the features of the signal that you're expecting. So once again, I know the frequency of my signal, and I like to zoom in. I believe it's around here. There's something here. Yeah, here you go. If you remember the 3 peaks before, here we see 3 peaks again. Out of curiosity, I would like to also zoom in on the polarization 2 data. And it seems that I wouldn't find any signal. Maybe if I zoom in very deeply, I might. But the point is, it was not that hard to find those 3 peaks. Another reason why there are 3 peaks that are transmitted is simply that the signal that is transmitted towards the Earth from Voyager 1 is a BPSK modulated signal. And this BPSK signal is pretty wide band. And usually a common practice in communication is to include a few very narrowband features to the signal to make it simply easier to lock your local oscillator to the data and make it easier to detect as well. So that's good for us. It's been easy to detect. Now, if I have a waterfall plot, what I could do as well is average it over all the number of all the different blocks, and let's see what that does. So I think I haven't written the code for that. I'll have to do it in my terminal. Okay. So this time I don't want to plot an image, but I want to plot an actual graph. It's only one dimensional. And I'll simply average my data along the blocks. Okay, here we go. Now what you see here is the power spectral density as a function of the frequencies. And as you can see, the noise really reduced a lot, because this time we're not averaging the data over 22 seconds divided by 128, but over 22 seconds. And of course, Green Bank, the Green Bank telescope is extremely sensitive. It's a 100-meter dish, and you would expect the signal to be detectable. But here it's detected in 22 seconds. That's pretty amazing. And you can even see further features that we were not able to pick before. Here there are a few other peaks. And yeah, that's pretty much it. So here is a central peak. This is Voyager, this is Voyager, this is Voyager, and a few other sidebands. So the normal frequency signature of a BPSK signal is some sort of sync shape. So here you would have a main lobe, here you have a side lobe, and we don't really recover this BPSK shape here. Because I should probably average the data over 5 minutes, but I guess you got the idea of what to do and how to do it now. But indeed, if you would do it, you would see the sync shape, and you would understand that those peaks just signal the presence of the side lobes, and those 3 peaks here signal the presence of the main lobe. So I think that's it for me. I hope you enjoyed this tutorial. I hope you understand a little bit more about raw files and about their importance in SLE search and for any science, really. We will be happy to get your feedback if there is any, or to answer your question. Here is my email address, and you can also simply contact the group at Berkeley. and we'll be happy to help you to provide you data and to help you manipulating them.